Hi, I'm David Bock, and I'm the director of the Loudoun Computer Science Initiative. We're a nonprofit in Loudoun County, Virginia, bringing extracurricular and supplemental education to Loudoun's K through 12 students. In our last video, we talked about the four facets of computer science education and how they build upon each other. And I promised that I'd do a video on each of these to go in depth as to what they are. Today we're going to be talking about computational thinking. When I talk about computational thinking with parents or students, they'll often ask, well, how is that different than normal thinking? And that's a really good question. And truthfully, it's not. It's just a subset of the kinds of thinking that we already do. If you're used to solving puzzles, then you're already on your way to understanding what the subjects of computational thinking are. In fact, I'm going to use puzzles to make some of them explicit. There are 5 different facets that we talk about with the topic of computational thinking. Today, we're going to talk about abstraction. We're going to start with a small card game. These are the face cards from a normal deck of cards. 16 altogether. 4 cards, Jack, Queen, King, Ace, of 4 suits. The spades, the diamonds, the clubs, and the hearts. We're going to lay these out in a square. So a 4x4 of all of the cards. And you can see here I already have this arranged so that every row is one suit and then the 4 cards from that suit in order. So let's ignore suits for a minute. Let's just talk faces and their values. So in every row, we have all 4 faces. In every column, though, we have all jacks, all queens, all kings, all aces. Is there a way we can arrange these cards so that in every row and every column, each face is represented once and exactly once? And yeah, the solution to that is pretty easy. We can just rotate them. And now we have Jack, Queen, King, Ace. It's not quite the same order. Of course, we're going to be changing the order of these things. But Jack, Queen, King, Ace are all represented. Jack, Queen, King, Ace all represented. Jack, Queen, King, Ace all represented. Same here. Jack, Queen, King, Ace. Jack, Queen, King, Ace. Jack, Queen, King, Ace. Jack, Queen, King, Ace. And at this point, people often say, oh, it's like Sudoku. And yeah, it's related in that it's a puzzle and it's based on a constraint. Many puzzles are based on constraints. Imagine jigsaw puzzles can only be put together a certain way. Even crossword puzzles, the words have to sync up in certain ways, and sometimes that's how you get the clue to what the next word is. So there's always a constraint in an interesting puzzle, and when the constraints are too difficult or too easy, it's not necessarily a good puzzle. Well, we've ignored suits so far. As you see here, I have one of each suit in each row, or in each column. But is there a way to have it so that we have all suits and faces represented exactly once in each column? Let's give it a shot and see what we can do. So this row is good, right? I like that row. So let's try to solve the top row. Queen. Well, what do we need here? That queen's not able to be used because we like this row. So let's take the queen of spades and let's just swap. So we have 2 hearts, 3 hearts. We need to get a king here. We don't have a club yet. And now that's going to leave only 1 ace that can go here because we have the 3. Oh, but it's in use down here. So you know what we can do? We can instead get the king of diamond. No, we can't because it's in use. Let's instead get the queen of diamonds. Oh, no, I had that right. We have the queen of spades up there. We don't need a spade. We need the queen. We need the ace of diamonds, and it's right here. See, I'm already messing it up. Okay, so we have a row here that's good and a row here that's good. I kind of like that king there. That king works because it's neither hearts, hearts. So what do we have to change here? Well, this ace and this ace are locked. We can't have 2 clubs. And, oh, we can't have a heart because of a heart. Okay, maybe I have to have the other king there. So let's switch the kings. Oh, but now I have 2 spades, and I liked that row, so I seem to be stuck. Well, So you wonder, is there a solution? Is this even possible? And yes, it is possible. There are thousands of solutions to this. When you play it, it takes maybe 20, 25 minutes for most people to find one. It's a really interesting puzzle. It's kind of fun when you start seeing the patterns of how to solve it, because there are thousands of solutions. And my own son in fifth grade, I showed this puzzle to him about 10 minutes before bedtime, and he started working on it, and then we had to send him to bed, and he was frustrated. Well, I got up at like 6 the next morning, and he had come down in the middle of the night and solved it. So I was proud of him for that, disobeying authority for something that he was an itch he had to scratch. I was really proud of him for that. So interesting puzzle here. But I ran into a problem with it once. I was showing it to a high school student at school, and he was uncomfortable due to personal reasons for dealing with cards. It said it looked like we were gambling, and it made me think, wow, I don't want anybody, when I'm dealing with my elementary school students to let them think that I'm teaching their kids to gamble. So I needed another solution to this problem. So we sat down and we talked about it, and we came up with that. This is a handout that I give to elementary school students and use in high school as well. And it is essentially the same problem. If you notice, I have 4 buildings: a house, a barn, a chicken coop, and a grain tower. And then 4 things that wander the farm. I have the farmer, the cow, the pig, and the chicken. And in each row and in each column, there is a complete farm. No building nor animal is represented twice in any one of those rows. So there's a solution to this problem. So you can see that the problems are essentially the same, just we've changed what we label the constraints. To illustrate what I mean by that, let me show you an example of what I mean. When we were first working with the cards, we could have written, let's say, the Jack of Hearts, the Queen of Spades, the King of Diamonds, and the Ace of Clubs. And then we could have said the Queen of Diamonds, the King of Hearts, the Ace of, can't have a diamond, it's got to be a club. Now you see it, that has to be a jack, and we know it has to be a diamond spade. So in some ways, this might be easier to work with than actually moving the cards around. Right? But there's nothing to say that every one of these has to be the symbols I'm using. I could just as easily change this to A1, B2, C3, D4. And go on like that. And that's essentially what I did. We call this in algorithmic design or data analysis, we call this semantic erasure. That's a larger topic, or a topic for further on than what we're dealing with now with abstraction. But the point is, I've erased some irrelevant details, but I still have the same construct, the same puzzle. Here's another puzzle, and I'll often use this with elementary school students along with either the farm puzzle or the card puzzle to illustrate this concept. And when students see these two puzzles side by side, they often intuit the concept of abstraction themselves. So let's talk about this puzzle. This is a 5 by 5 square, and there are 5 colors: blue, green, yellow, orange, red, and 5 heights from the tallest all the way down to the shortest. So the objective of this is to get a height represented in each row and a color represented in each row. So all heights and all colors represented in every row. And you can already see that I have all the colors represented in this row, but not all the heights. So let's just do the obvious thing here. So there's at least one row here on the back. Here, let me turn this around. That has every height and every row represented. So the objective is to do that for all rows and all columns. And this is much more challenging than the 4x4. So the question is, with students, how is this puzzle like the other one? And of course, we'll get that same, oh, it's like Sudoku answer. Yeah, but I'm looking for something a little more descriptive than that. Because a lot of things are like Sudoku. This is much different, really. And we start talking, well, this one has colors and that one has farm animals. And I was like, yeah, but is that relevant to the problem? And some students will say yes, and some students will say no. And through a series of leading questions and some provided answers, the students will eventually realize that, well, that puzzle has 4 things in each category. This puzzle has 5 things in each category. So they've abstracted away the colors, the animals, the faces, the suits, the heights, and we're left with just what's different about these puzzles. It's the same concept, just one is of order 4, one is of order 5. What's interesting from a historical perspective with this puzzle, this is called a mutually orthogonal Latin square, and I can introduce it to students at a very young age, but when we get into high school age, this becomes a much more interesting math problem, in that I can easily prove to you that with, let's say, 2 heights and 2 colors, there are no solutions possible. Because now I have, a height in each row. The heights are different. Oh, but the colors aren't the same. Or the colors aren't meeting that constraint. So now I try to make the colors match the constraint, and the heights are the same. So for order 2, there are no solutions, and I can easily prove that to you. And hundreds of years ago, the mathematician Leonard Euler proved that there were none for solution order 6. Interesting problem, in that there are none for 2, there are plenty for 4 and 5, none for 6, some for 7, 8, and going on up. And Leonard Euler thought, well, maybe there are none for 10. Let me try to prove that. And he worked tirelessly for a large portion of his life to try to prove either that there were none for 10 or that ones for 10 existed. And he couldn't prove it. And for hundreds of years, mathematicians just presumed that there were none of order 10. It was just a hard thing to prove. And eventually, they found a counterexample. One of order 10 was found by a computer search in 1963. And that's an interesting problem at the high school level. Let's show some solutions for that. So I have here a computer program that we take apart in high school and see how it works. And this is searching for orthogonal Latin squares of order 10. Now, mind you, mathematicians searched for hundreds of years and didn't find any. And until 1963, it was thought that the space was so large and the problem of trying to just brute force constructing them was so hard that it would take a computer tens of thousands of years to solve it. And in 1963, there was a breakthrough in the understanding of the problem that led to a computer solution that they could find one every several hours. Well, as you can see, I just found one in a couple of seconds. And the field of solutions is so large, we have math to determine this now. The solution field is so large that the solutions you're seeing here are probably unique, have probably never been seen on the face of the planet before. I think that's pretty cool. And now, of course, we can search them and find them, and pretty quickly. So that's the concept of abstraction, in that we take a simple puzzle like this, and we look at how we can represent it with various semantics. The color, the height, the suit, the face, the barn, or the buildings, and the animals. And we can find many different variants of this. This is also a famous scheduling problem, in that we need to pair teams and stadiums and referees together. It's the same kind of problem. And for some of them, there are no solutions, which is why we often have bye weeks in schedules. By stripping away all of the semantics of the problem, we can get to just what the crux of the problem is, the constraint and the order 4, order 5, order 7, and describe the problem in even a little notation that allows us to expand that. So that's abstraction. I'll be doing videos on the other topics very shortly. Thank you very much.